something a little bit different here, and rather than looking at just from the atmosphere, I'm going to be looking more at sort of the sources for that from biology and the magnitude of the biosphere and how that might impact the signal that we could expect. And we're going to do that by looking at oxygenic photosynthesis and its productivity. And we're going to start with the modern Earth, right? Everyone's favorite planet. And we learned yesterday, right, not to use the term Earth-like, and I'm going to use that all the time throughout this talk. But in this case, I actually mean exactly that planet. So when I say Earth-like, I mean it's got oceans, it's got continents, it's the same thing. So hopefully that's an acceptable use of the term Earth-like. And when we look right at the Earth biosphere, we see that it has this massive primary productivity, right? 10 to the 14 kilograms a year, which is a huge amount of biomass that's produced every year. And that's a hard number to think about, so I figured I'd put it in terms of space needles. And if you haven't been there, it's a pretty cool building, and it has a rotating restaurant on the top. And as of last year, there's a glass floor. So if you like getting motion sickness while you eat, you know where to go. And in terms of these space needle masses, right, it's about 10 million space needles worth of biomass, roughly, is what's being produced every year on the Earth, that's a huge amount of organic matter. And all of this organic matter is coming from oxygenic photosynthesis. And that's powered right by the sun, which is giving us this huge amount of energy, this 1,300 watts per meter squared at about 1 AU. And as we've heard throughout the week, this productivity, right, is not limited by energy input, right? There's plenty of photons to go around for everybody, for the most part, in the biosphere. And rather, this overall growth is limited by phosphorus or nitrogen availability, with phosphorus probably being the limiting nutrient throughout much of Earth's history. And we can look at this a little bit more deeply and look at the distribution of biomass productivity. And we see that about 50% is generated on land in places like these nice rainforests, and the other half is coming from the oceans. And this whole process rate is controlled by the amount of phosphorus, or I guess the amount of this oxygenic photosynthesis is controlled by what we can weather from continents like mountains like these. And so what we want to know is, how does this differ around other stars? Right? If we were to change the type of star that the Earth is orbiting, then could we end up sort of breaking this regime that we have going where we're limited by phosphorus availability and potentially become limited by photon availability, and so the energy input to the system? And we want to be able to answer that not only for just changing the type of star, but maybe if we move the Earth further out around our sun, could we encounter this same problem? And before we get to that, I think it's worth just mentioning, do we need oxygenic photosynthesis? Could we sustain a comparably sized biosphere with just chemical energy alone? And the answer is probably not, right? If all we have are these hydrothermal vents or something like that, the amount of energy coming out is so much smaller that it would be difficult to imagine a way to sustain a comparable biosphere. But as we heard from Josh, that may not make it undetectable. Perhaps there is still a way. But if we consider detectability as sort of scaling with size of the biosphere, which might be a reasonable thing to think, then oxygenic photosynthesis is really the best thing we could come up with, the best metabolism to get these massive biospheres like we have on the modern Earth. And we can think of sort of the energy that the Earth could provide to a potential biosphere without oxygenic photosynthesis. And if we said, oh, well, all the energy coming out of the Earth, if that could somehow be captured by biology, the total energy is just a tiny percent. And Josh actually mentioned in his talk, right, that the early Earth is thought to have potentially been limited in this sort of way. And on the very early Earth, the total biosphere may have been less than 1%, 0.01% of the modern biosphere. So very, very tiny. And so hopefully we're convinced, right, that oxygenic photosynthesis, we have that nice equation up there, is necessary. And so at this point, we've heard this a number of times, right? We take CO2 and water, and here I just have our collection of photons, and I've left the nutrient term off, but that would be up here, right? That's our limiting component here. And when we look at this for the Earth, since, right, I'm assuming for most of this talk, we're just going to be talking about the Earth, then we have plenty of water, right? We're not limited, and we have plenty of CO2. And those are probably reasonable things to think for Earth-like planets around other stars, right? Because we're assuming they're habitable, so they've got water, and there's probably CO2 on these terrestrial planets. And so of this biomass that's produced, right, that 10 to the 14 kilograms a year, well, we can look at how many photons are being used for that. And so if we look in the oceans, we see it's about 7% of the photons in the visible range that are used by photosynthesis get taken in for this process. And on land, it's a little bit higher at about 31%. And it's worth noting that these numbers are a little uncertain because those are hard to measure. So just take that with a grain of salt. But to a first order, these are sort of the numbers that we're looking at. And so we'd like to know, right, if we look at these photon uses for the Earth, and we look at that equation up there, can we get to the point where that photon term becomes the limiting term in terms of biomass productivity? And we can first ask that question for the Earth around the sun. And that's what you're seeing here. So here we have the sun right here, and we're looking at distance from the star on the horizontal axis. And I've shown the habitable zone, which hopefully you can see in the back in this faintly shaded purple-blue region, a conservative habitable zone, right, with the Earth right at the inner edge there in gray. So our solar system planets are in gray. And if you took the Earth and you started dragging it outwards, when you hit that green dot right there around 2 AU, that's when you would no longer have enough photons to sustain the terrestrial biosphere, right? So at this point, the growth of your biosphere is going to be limited by photon availability. It no longer matters that we have enough phosphorus. We could no longer sustain, say, the rainforests of the modern Earth. And if you were to drag the Earth all the way out to that blue dot that you see around 4 AU, that's the distance at which the oceans would no longer have enough photons for growth. And you might say, of course, that I've cheated here, right? Because I made the assumption that water was going to be abundant, and you would be right. You know, by the time we've pulled the Earth out to here, it's frozen over. So it doesn't matter that there aren't enough photons. Nothing's going to happen. And it's even more of a popsicle, right? By 4 AU, there's no chance that we're going to be having an ocean there. And I think that's the important thing from this figure, right? Is that for a sun-like star with an Earth-like planet, it's unlikely that you can be in this light-limited regime inside the habitable zone, right? If you have a comparable nutrient flux from continents. But then it becomes a really important question, right? Is what happens as you decrease the temperature of the central star, right? The habitable zone is going to move in, but more importantly, the type of photons, right, that the star is putting out are going to change. So I like this figure from Wikipedia, where we can look at the sun spectra, and they do a really nice job of coloring it to make it pretty. And if you're not familiar, right, with stars and how they work, right, as you decrease the temperature, the peak of the photon flux is going to start shifting that way into the infrared. And when we think about photosynthesis, it's using photons in this range right here. And we'll talk a little bit more about whether that range is just because we're on Earth, or if that's actually a hard requirement. But if we were to think, say, well, photosynthesis has to use this range, and you started moving that curve to the infrared, then the number of photons are going to become limiting, even though the total energy input could remain the same. And on Earth, right, those limits for photosynthesis, it's about 400 nanometers on the lower end, and about 750 nanometers on the upper end. So those are the photons that can be used in that reaction that we've looked at so many times. And if we look at the lower limit, that's probably a reasonable lower limit for the photons that can be used. Below about 400 nanometers, the photons are energetic enough that you can start ionizing your pigments, and obviously that's bad for life. You don't want to have that happen. So that's probably a reasonable lower limit for Earth and other planets should they evolve oxygenic photosynthesis. And the upper limit, though, is much less certain. On Earth, it's observed to be at about 750 nanometers, but it's not really certain if that is the case because, as we see here, right, there's plenty of photons, as we know, on Earth. So perhaps there's just no selective pressure, right, to use the photons out there for oxygenic photosynthesis because there's plenty in the visible range. Or it could be that there's some other limit that we don't fully understand at the moment that prevents oxygenic photosynthesis from using longer wavelength photons. And so now if we look at spectra of other stars, we can now think about this in a little more detail. And so hopefully you can see all these squiggly lines, and I know there are a lot of them, and it's a little difficult to read. So hopefully you can pick out this nice orangish yellow one. That is the sun spectra at the surface of the Earth. And what you'll notice, right, is that we have our visible range. And if we look at sort of the photons there, right, we see that most of our photons are coming in that range. So as we would expect, that is where our photosynthetic organisms are absorbing. And so I want to draw your attention, though, to this pink line and the green line down here. And if we look at the key, we can see that those are much cooler stars. That's the spectra that the Earth would have if you were to put it around a cooler star. And what you'll notice, right, is that in the visible spectrum, right, we have very few photons. And actually, the photon flux, if you sort of imagine that you could smooth out that green curve or the pink curve, right, it's peaking in the infrared. And so if the same selective pressure exists on other planets to evolve photosynthetic organisms that are optimized, perhaps, right, to that peak photon flux, then we would probably expect photosynthetic organisms to evolve, right, to absorb maybe in this range where there's the most photons available for that reaction to occur. And we can actually calculate, more approximate where we might expect pigments to be tuned around other planets based on the stellar type. And so that's what you're looking at here. So if you take stellar temperature and then you start calculating the optimal pigment at which you would expect pigments to be tuned to, or the optimal wavelength, sorry, for pigments to be tuned to, you generate a curve that looks like this. And so we set for the sun, we're way over there, and then we're right around the right mark at about 700 nanometers, where we would expect pigments to be tuned, which is indeed where chlorophyll A is roughly tuned to. And the important thing, though, is to look at these much cooler stars, right, as this curve starts turning up. And by the time you hit these M-dwarf stars, right, you're past about a micron. And as you go to a star like TRAPPIST-1, you're almost at 1.5 microns is where you would expect photosynthetic organisms to absorb if they're optimized for that peak photon flux. And this, of course, can present somewhat of a problem. But how much of a problem? And that really comes back to the photosynthetic pathway. And so Bob did a really nice job of going through this earlier in the week. And so that's what we're going to look at just in a little bit more detail, right, is this two-step Z scheme. And it's called, all right, if you turn your head to the side and you squint, you see a nice Z shape there with the green bits. And the problem here with using those longer wavelength photons, right, is these jumps right here, because the goal is to get, in terms of energy, which you're seeing vertically here, is you need to get from down here to that same energy level. And so when you're using visible wavelength photons, right, you have a photon come in, you get that energetic kick, and then it goes down, you get a second photon, and you get a second input of energy. But what happens if you're using a 1.5 micron photon, right? Then the energy kick that you're going to get might only take you up a fraction of the way that you need to go. And in theory, you could just keep adding more steps in here, right? So if you want to make it up to there and your photons only have this much energy, why not just start adding more and more steps into the process? And so in theory, that is something that could potentially be done. In practice, that may not be possible, right? When you think about the complexity of this metabolism and that it only arose once, is it feasible to think, right, about maybe adding in a third step or a fourth or a fifth or even up to a sixth step, which could be required for these really long wavelengths that you would want to use around those cooler stars? And so we can actually try and put a few other limits on the photons that might be usable by the biosphere. And so if we look at, say, a water molecule, a limit that's often proposed is that you need about a 1 micron photon, which corresponds to the energy, roughly, that you would need to pull an electron off of water, off that nice molecule there. But this is actually a common misconception, right, that you need a photon that can directly pull that electron off. And in fact, right, you just need to be able to excite the pigment. And so really, all that we need for something like chlorophyll A that you see here, right, is you need an electronic excitation. You need to be able to kick that electron up to a higher energy level in your pigment. And then you need to get the same total energy output from the system, right? We sort of saw in that two-step Z scheme, we need to be able to move up that energy slope to get enough energy to pull the electron off water. But you could imagine, right, that you could potentially restructure this molecule and get it to absorb at a different wavelength, which, as Bob mentioned, has been done in the lab, that you can actually make pigments that absorb at other wavelengths pretty much arbitrarily. So we can then sort of take our understanding of photosynthesis, and even though we don't know exactly how long the wavelength could be, we can come up with some plausible limits, and then look at how each of these limits could impact the total biosphere productivity, right, which is what we want to address. So if we took the limit on the modern Earth as being the hard and fast limit for oxygenic photosynthesis at 750 nanometers, that's not perhaps an unreasonable place to start. So we'll use that as our first limit, and in a moment we'll be comparing how these different limits affect the biosphere size. A second limit was actually found at around 900 nanometers, and this was from looking at oxygenic photosynthesis as a thermodynamic system where the back reaction at night becomes more efficient than the forward reaction during the day. So if you tune your pigments beyond about 900 nanometers, you would end up losing energy. So the idea is that you might not expect pigments to be tuned beyond that wavelength if you're in fact exposed to that diurnal cycle. If your planet, of course, is synchronously rotating, then maybe you don't have that issue because you'll never be in that nighttime regime. A third limit that I think is pretty reasonable is at about 1100 nanometers. And I think this is perhaps the best case upper limit. And that is the limit of an electronic excitation that we can detect with the best man-made sensors. And so you could argue, right, that this is just a limit of human ingenuity, and perhaps we can make a better sensor that could detect an electronic excitation with a longer wavelength. But biology seems to have hit a similar limit. And even for anoxygenic photosynthesis, the longest wavelength that can be used is just past 1 micron, right around the same place. And then we'll consider one more limit at 1500 nanometers, which is perhaps not super reasonable, but it'll just be sort of the upper bound, right? And that's beyond where we would expect pigments to absorb even around a star like TRAPPIST-1. And so we'll just throw that in just so we can compare it. Now, if you'll recall right from when we looked at the Z scheme, that if we're using these longer wavelength photons, right, we need more steps to get the same amount of energy in the system. And we need to have the same amount of energy, right, to pull the electron off of water for oxygenic photosynthesis. So if we wanted to use photons up to just past 1 micron, well, we need 3 steps in that pathway. If we want to go up to 1400 nanometers, you need 4 steps. And if you want to be able to use photons, at 1500 nanometers or all the way up to 2100 nanometers, you need 6 steps. And so just thinking about the complexity of evolving that system is pretty daunting. So whether or not these are actually possible, maybe not. But in theory, could they evolve, then this is what you'd need. So now we can take these limits and we can plot the total biosphere productivity in these plots here. So what you're looking at here is the 4 different limits that we considered for the long wavelength limit that's usable in oxygenic photosynthesis. Right? We have 750 nanometers, 900 nanometers in B, and then our 1100 nanometer limit and the 1500 nanometer limit down there in D. And what you're looking at, right, is stellar temperature on the vertical axis, and the habitable zone is drawn in with the black lines for you. And the red shaded region is showing you regions around the star for a given temperature where the photon flux is below the ocean use. So any planet that you see that falls in this red shaded region here does not have enough energy to sustain the modern Earth's ocean biosphere. And anything that's falling in the blue shaded region does not have enough energy to sustain the terrestrial biosphere. And so when you look at this, right, it doesn't bode super well for perhaps some of these really cold stars if they are indeed Earth-like, right? When you hit about 3000 Kelvin, then you see that a lot of these planets could be growth limited by light. And then a bit later, I'll address how detectable that makes these potential biospheres. And there's one other feature that I want to point out, which is what happens to photons in water. And I think this is really important when we can think about that long wavelength limit, because if we wanted to look at oxygenic photosynthesis in water, here are those same spectra that we saw earlier for several different stars at different temperatures. And now we're just at 5 centimeters depth in water. And if you recall before, these curves went all the way out, way past into the infrared. And now, just at 5 centimeters depth, right, everything past about 1 micron is more or less gone, and it's absorbed by water. And as you go just a little bit deeper into the water column, which is what you're looking at over here, right, by the time you hit 1 meter, I don't know if you can see that dashed ray. You probably can't, so just take my word for it. That curve goes down, and you drop, right there at around 900, 950 nanometers. And everything beyond that is just simply gone. So if we look back to the plots here, right, this plot B is perhaps the most reasonable as our upper limit if we think about life in water. And that may be a good spot for us to consider total biosphere productivity, just because any photons beyond that are likely going to be very scarce in water-rich worlds, which is the ones, right, that we're most interested in. So if biospheres can be less productive around cooler stars, then how detectable does that make them, and how can that inform our target selection? And so throughout the week, we've heard a fair amount about cycles on the Earth, and particularly how oxygen is produced. So I just want to spend a few moments pointing out the important aspects there as a review, and then we can look at how that impacts these biospheres. So recall that almost all the oxygen that's produced from oxygenic photosynthesis, right, gets consumed almost immediately by respiration and oxidative decay. And the only oxygen that builds up in the atmosphere is the oxygen that is sort of liberated and that can't re-react with the organic matter, and that organic matter is buried and removed from the system. And the estimates for that are a little uncertain, but about 5 to 10 teramoles a year in organic carbon burial, which corresponds, right, to moles of oxygen. That's sort of our flux to the atmosphere. And of course, if we look at the modern Earth, right, there is not this oxidation, Earth's oxygen isn't increasing at 5 to 10 teramoles per year, and rather we're in more or less a steady state. And that's because the O2 that's produced from this organic carbon burial is removed from the atmosphere by reducing gases from volcanism, like hydrogen and carbon monoxide, and then the remaining sort of surplus is weathered out of the system via continental weathering. And so we can look at that graphically, which I think helps. So we have our source of oxygen, right, from this organic carbon burial. You could get a little bit from hydrogen escape to space, but most of what we're interested in, right, is this organic carbon burial term. That's our main input here. And then it's going to be drawn down by these gas fluxes. So from volcanism or from submarine volcanism, we can get these reducing gases that draw down atmospheric oxygen. And so on the Earth, the flux, right, of those reducing gases is on the same order. It's about 5 to 6 teramoles a year of these reducing gases that come out to consume oxygen. So if we take that reducing flux from the Earth and we say, all right, let's think of an Earth-like planet with the exact same reducing gas flux of, say, 6 teramoles a year, then how much oxygen could a planet produce if its biosphere is limited? And could it build up an oxygen-rich atmosphere that we could detect as a biosignature? And so that's what we're looking at here with these bluish-green colors. So we're looking at oxygen production from organic carbon burial as a fraction of modern Earth. That's what the colors are showing you. So blue means very little oxygen compared to the modern Earth, and that very light green means it's the same. And so what I've drawn on here for you are these two contours. We have a dashed contour, and the dashed contour is showing you if you took sort of the best case scenario for organic carbon burial on the Earth, which is about 0.3%. If you say 0.3% of the organic carbon that's produced gets buried and removed from the system, then your oxygen flux is enough if you fall above this line. That means that your oxygen flux is more than the reducing gas flux from the planet. So if we look at this plot here, everything above this dashed line could build up oxygen from oxygenic photosynthesis over time. But anything that falls below this line is producing less oxygen than the reducing gas flux from the planet. And that doesn't bode well, right, for building up an oxygen-rich atmosphere, because you'll never be able to accumulate your atmospheric oxygen because it's being drawn down by natural planetary processes. And so this is sort of the best case scenario line, right, this dashed line here. However, if we just took the median estimate for organic carbon burial on the Earth, it's that dotted line. And then things look a little bit less ideal for having oxygen build up on these planets, right? Anything that's falling below that line would be producing less oxygen than the reducing gas flux from the planetary interior. And so if we wanted to think about this, right, in terms of biosignatures, then it may be very difficult for stars with temperatures between this trappist temperature and maybe up to about 3,000 Kelvin to produce large enough biospheres that we could expect an oxygen-rich atmosphere to form. And there's one other feature that I think is really important to point out, because of course we assumed an Earth-like reducing gas flux there, and we really don't have a good idea of what a reducing gas flux could be on another planet. It could be a lot higher, it could be a lot lower. And so even if we sort of take that out of the picture for the moment, I think it's also really important to look at just the total crustal sink that exists on the Earth and could exist on other planets. And so if we just think about all the oxygen that's stored in the crust and how much has that been over time, we come up with a number of about 10 to the 10th moles. So that's a lot of oxygen, right, that's sort of been sunk or could have been put into the crust. And right, if we compare that to the roughly 10 teramoles a year that's produced on the modern Earth in terms of oxygen, we can see right that is maybe billions of years potentially of oxygen that could be consumed by the crust. And something like this may have happened on the Earth, right? If we look at the evidence for when oxygenic photosynthesis evolves, we see that there's pretty good evidence that oxygenic photosynthesis was operating by about 2.7 billion years ago. But as we saw earlier in the week, maybe as early as 3 billion years ago, and there's even some tenuous evidence all the way back into the Archean, the early Archean, that oxygenic photosynthesis may have been present. And when we look at the great oxidation of the Earth, then there may have been this sort of 300 million year period, right, where we have oxygenic photosynthesis and we don't have this oxidized atmosphere, and so that crustal sink could be really important. So even if we ignore the reducing gas flux from planets, if they have a similar crustal sink to the Earth, and maybe their productivity, so that oxygen that they're producing is not being consumed by reducing gas fluxes, but if it's still only a fraction of modern Earth's productivity, then what took maybe 300 million years on the Earth could take billions of years on another planet, right, to overcome that crustal sink for oxygen, to be able to build up atmospheric oxygen. So I think it's really important to keep that in mind. And even though we've been focusing on the Earth throughout this talk, these same principles could apply to other planets with different burial rates and sort of different structures. And so it's just really important to consider that the biomass productivity could be just a few percent of Earth. And so that doesn't make them impossible to have biosignatures, but it's definitely something that could be concerning, especially when you consider the outgassing rates on these planets. And so I just want to end here with a few thoughts on target selection, which I know Vicky did a really nice job in the first day sort of describing that M dwarfs are hard, and we're going to have to look at them anyway. So that sounds good. We're going to look at them, but I wanted to maybe plug that we should really be looking at these FGK stars, right? If we want to find Earth-like biospheres, those sound great. And in order to do that, a telescope like LUVOIR just seems like the perfect solution. So if you're unsure which is your favorite, that should be it. All right, so I'll leave this up here, and I will take any questions. Thank you.
Very good presentation. I really appreciated looking planets and the wavelength that they were had some that are large emissions that are. I guess I'm just kind of thinking about is it possible with just 2 photon absorption photosynthesis? So you have like you absorb 2 photons at like I don't know 1,000 nanometers.
So are you asking at the same time, so when you think back to, actually we could pull up the Z scheme here. So are you asking that you want to absorb 2 photons simultaneously in a photosystem? So you have like 2 spin. So I do not believe that is possible, and I'm not really a great quantum person, but I'm pretty sure you're not allowed to absorb multiple photons to 1 electron. I'm not 100%. Maybe Nikki would probably know better, but I don't think that can happen. So really, you really need multiple steps where you'd have to be building up a more and more complex system in order to use those longer wavelength photons.
Sorry. We'll grab off the first thing.
How do you determine how many steps are required depending on the photon?
So that comes from some work from Nancy Chiang, where she was looking at the photon energies and just trying to calculate the sort of the loss that occurs in the absorption. If you assume the same, then you could sort of move up. If you don't go up these steps, then if you look at the energy in a longer wavelength photon and how much of that energy you expect to be turned into the energy in the system, then if you want to get the same total energy, then you can calculate how many photons you need to absorb, and that tells you how many steps you need. This one here is for oxygenic photosynthesis and what's happening on Earth and plants right now.
I guess there's something I don't quite understand. I mean, on the Earth, I think I've heard this week that there's more energy than we need. That there's more energy available, more light energy available than biosphere needs. So I guess I don't understand why you would think that the light harvesting machine would be at the peak with the photon flux.
Yeah. So for the modern Earth, that's a great point, and that's been pointed out before that may not be why those overlap, because as you just say, right, there's plenty of energy. So why is it that they don't use a broader range? And so the 400 nanometer limit, right? That's why that one's probably a reasonable expectation that you don't want to be ionizing your pigments. But the longer wavelength, it's very uncertain why it should stop at about 700 to 750 nanometers. And so if you have a thought on that and could come up with a solution, that would be fabulous.
I'm thinking about photosynthesis on tidally locked planets. So if there is photosynthesis on the day side, it does not have to produce as much organic matter to store for the nighttime use when light is not available. Would there be a fundamental change to the mechanism of photosynthesis? And also, maybe there will be less organic matter burial and there will be no oxygen buildup.
So that's actually a great question. That's not something that I've actually thought about before, is how the biomass would change if it was tidally locked and you didn't need to store organic carbon perhaps as quickly. Nikki might be the better person to answer that.
Yeah, it's a great question. One thing you have to think about, though, on the synchronously rotating planets, if you're under constant illumination, there's nasty things that get produced during oxygenic photosynthesis, such as reactive oxygen species. You're going to have to figure out a way to do that. So life might be, at least oxygenic photosynthesis might be